Welcome to lecture number 19 for EE206 Circuits 1, Mutual Inductance. Now, inductors are different than capacitors. With capacitors, they deal with electric fields. Electric fields have a start and an end. There's such a thing as a plus charge and a minus charge. What that does is when you have a capacitor, like a parallel plate capacitor, I can put plus charges on one plate, minus charges on the other plate, and the electric fields have a starting point and ending point. Very small part of the electric field goes outside the capacitor. This allows you to put capacitors in circuits without having any coupling between them. That's not true with inductors. There is no such thing as a magnetic monopole, so all magnetic fields never have a starting point, they never have an ending point. It's got to be a closed path. What that does is it makes magnetic fields much more difficult to contain. If the field of two inductors overlap, the two inductors affect each other. That's called mutual inductance. Sometimes that's bad, sometimes that's good. In the case of transformers and motors, that's good. That's how they work. For example, suppose I want to have two inductors on the same iron core. The first inductor produces magnetic flux proportional to the amps times number of turns. The units of magnetic flux are amp turns. If this is an iron core, almost all the flux will go through the iron core through the second inductor. So the amp turns on the first winding are equal to the amp turns times the second winding. Now there's a thing called the coupling factor K. If K equals 1, like for a transformer, almost all the flux lines through one inductor goes through the other. What that means is that the amp turns times 1 equals amp turns times 2. They're highly coupled. If I have two inductors in the same circuit and just a few of the flux lines interact, I have K between 0 and 1, that's mutual inductance. If I take the inductor and rotate it 90 degrees so that they're perpendicular, now the flux lines no longer interact, and their K equals 0. So that makes designing circuits with inductors kind of a nuisance. It depends upon where you place the inductors on the circuit, how you place them on the circuit, their orientation, their distances. All that affects how inductors behave on a circuit, which is one of the reasons we try to avoid inductors if at all possible. To model mutual inductance, you take the two inductors L1 and L2, and the mutual inductance is that K factor times the square root of the two. This would be the model that you use for mutual inductance between two transformers. Now there's a couple circuits where you really want mutual inductance. A prime example would be a transformer. Here the transformer is an inductor, actually two inductors, that share a common iron core. Almost all the magnetic flux that goes through one inductor goes through the other one. What that does for you, that forces the flux in 1 to be the flux in 2. Flux is amp turns, N1I1 equals N2I2. Or the current I2 is just a scalar factor times the current I1. If I make this a 10-to-1 ratio, this side is 10 turns for every turn over here. I'm going to get 10 times the current on the second side. Power has to balance. Energy always has to balance. Energy is volts times amps. So that means if the current is going up by 10 times, the voltage has to drop by 10 times. And the voltage kind of makes sense. If I have 10 windings over here, one winding on the right, 10 volts on the left produces 1 volt on the right. So transformers are a way to change currents and voltages. That only works for AC though. The voltage induced for an inductor is V equals L di dt. The current has to be time changing to get a voltage, which means that for a transformer, transformers work for AC, where the current's changing. They don't work at DC. That's why the power grid uses AC, because transformers work at AC. That's why we use 60 Hertz. To illustrate why that's important, suppose I want to transmit power from western North Dakota to Minneapolis, about 1,000 kilometers away. If I have 1 centimeter diameter copper wire, 1,000 kilometers of 1 centimeter diameter copper wire is 213 ohms. And that may not seem like a lot, but suppose I want to transmit 12 kilowatts to Minneapolis. 12 kilowatts at 120 volts is 1.2 ohms. If I'll take that 213 ohm copper wire and transmit power from western Dakota to Minneapolis, to get 12 kilowatts to Minneapolis, I've got to transmit 21 or 2000 kilowatts. The current is 100 amps. The transmission line losses are I squared R. That means this 213 ohms will be dissipating 2000 kilowatts just to get 12 kilowatts to the customer. The efficiency of this system is 0.0005 or 0.056%. This is why we don't use DC. With DC, you just can't transmit power over large distances unless you bump up the voltage. And DC voltages are difficult to bump up. It can be done, but it's not easy. That was Edison's solution. Tesla came up with the idea of using an AC power grid. With AC, I can use transformers, take the 120 volts, bump it up to 120,000 volts, transmits the power per 1,000 kilometers at 120 kilovolts, bump it back down to 120 volts, and then have that go to your house. Now, by using transformers, when the voltage goes up by 1,000 times, the current goes down by 1,000 times. So the 100 amps over here that the customer sees is only 0.1 amp on the transmission line. The transmission line losses are then I squared R, 2.13 watts. So the total power I have to produce is the 1.2 kilowatts plus 2.31 watts. That's how much power I have to produce. Of that power, 99.8% of it gets to the customer. Only 0.0 or 0.2% gets burned up in the transmission line losses. That's what you can do with transformers. I can change the voltage very easily just using a transformer. And that's why our power grid uses 60 Hertz rather than DC. Transformers don't work at DC. At 60 Hertz, however, they do work, and I can do these tricks. Bump up the voltage, transmit it over long distances, and then when you get to your house, bump it back down. Transformers also change the impedance. If I look at a transformer, the voltages on the secondary side are N2 over N1 times V1. The current is N1 over N2 times I1. The resistance is voltage over amp. If I have a resistance on side 2, V2 over I2, then seen over here on the left on side 1 is going to be N2 over N1 squared times R1. So when I look, just kind of goes the other way around. When I look at impedance over here, if I have an impedance on the R1 side, what I see over here on the second side, R2, is where you're going to divided by where we're coming from squared. So if this is a 10 to 1 transformer, 1 ohm over here times 10 to 1 becomes 100 ohms. Where that's used is in some of the old stereos. If you ever find a stereo at your parents' or grandparents' house that just weighs a ton, probably what's happening is they have an inductor in that, or a transformer in that stereo. And the problem they're trying to solve is this. If I build an amplifier with transistors or vacuum tubes, you tend to have a high output impedance, say 100 ohms. If I take this stereo with 100 ohm output impedance, again this is the Thevenin equivalent of the stereo, looking at the output, connect an 8 ohm speaker to it, then what happens is if I want to have 10 volts across the speaker, 1.25 amps, then the power dissipated over here is 156 watts, I squared R. So I'm actually producing the sum of the two, 168 watts to get 12 watts of the speaker. I'm only 7% efficient. This is a great way to heat up your house, not a great way to produce sound. Instead, if I use a transformer at the output, the impedance seen through a transformer goes up as the turn ratio squared. This 8 ohms looks like 8 times 10 to 1 squared. This looks like 800 ohms at the stereo. 800 ohms relative to 100 ohms increases the efficiency up to 89%. Or in terms of energy, if I have 1.25 amps over here, I've got 1/10 of that over here, 0.125 amps. The losses are I squared R, so the efficiency is the power to the load divided by the total power, again 89%. So transformers help increase the efficiencies of things like stereos. It's a buffer that goes between low impedance and high impedance. The cost, however, is that to get 10 volts to the speaker, I need 100 volts inside the stereo. So if you ever see a stereo that just weighs a ton, it has transformers in it, don't put your hands on the inside. The insides can be hundreds or thousands of volts. And I need that to produce the current at the speaker. Another example of where transformers are used are the AC induction motors. Now, to illustrate how motors work, if I take a coil and rotate it around a magnetic field, I produce current, and the current I'm going to get is a sine wave. If I leave it open, I get a voltage. So naturally, if you have a rotating coil in a magnetic field, I get an AC sine wave. From duality, if I apply a sine wave to the voltage, it spins. So motors and generators are one and the same thing. If I spin a coil, I get a generator. If I apply voltage, I get a motor. That's an AC motor. What DC motors look like, DC motors have this commutator. When I go through the zero crossing, I flip the leads. And what that does is, instead of getting a plus minus voltage, I always get a plus voltage. So this is a DC generator. It has the average DC value. This is also a DC motor. Apply constant voltage and it'll spin. And this also shows that motors and inductors are inherently coupled. This coil right here means you have an inductor. A coil with current is inductance. An AC induction motor, this is actually a permanent magnet motor, uses a single line of AC and outputs cosine and sine. The impedance of capacitor, capacitors differentiate. And if you take the derivative of sine, you get cosine. So by going from cosine on one axis, sine to the other axis, I get a rotating magnetic field. Have a permanent magnet in the middle, that's the rotor, and it'll follow that rotating magnetic field. That's a single-phase AC motor. That's low power. The higher power AC motors actually use three-phase. If I have three-phase voltages going around the circuit, that produces a rotating magnetic field. This is an induction motor. This is basically a conductor in an iron core. That's a single turn for a motor. If I have an n-to-1 turn ratio, the current induced goes up as n-to-1. So this is 100-to-1, I have 100 times the current. Current through a coil produces a magnetic field. That magnetic field will cause torque, fight with the other rotating magnetic field. Synchronous speed is when the two are rotating at the same speed. When this is rotating at the same speed as the rotating field, that synchronous speed, there's no relative changing voltage relative to the rotor, and the current goes to zero. That's kind of how induction motors work. I've got an n-to-1 transformer inducing current in the motor. And what that means is when you model AC induction motors, you're really modeling a transformer. I've got the stator side, an n-turn n-turn of the transformer. I've got the rotor, which is a single turn for an n-to-1 transformer. The only difference is there's an air gap in the transformer. This can rotate. It follows the rotating magnetic field. So the mathematics that you're going to be using to describe RL circuits works for transformers, they work for AC induction motors, they work for pretty much all motors. And that's covered in detail in ECE 331 energy conversion. For now, for this class, just understand that inductors produce voltage where V is L di dt. The change in current produces a voltage. That's lecture number 19 for EE206, Circuits 1.